Okay, so now we get to the numerical part, how you actually compute those eigenvalues and why you need to compute those eigenvalues, things of that kind. And motivation, as I mentioned before, briefly, to compute eigenvalues as we did before, you need to compute determinant. And if you have order of like 100 by 100, it's already complicated because computation of determinants based on the n-1 determinant. And this one is n-2. This one, like, you have like billions of them. You cannot computationally compute it actually in the computers in any normal time, right? And sometimes you have matrices to like really huge order. And we will see some of the examples like that later. So it's computationally too expensive and you need to do something about it. You still need to compute eigenvalues because this is very important to multiple different algorithms. Another thing, sometimes you have that kind of matrices, so clearly you will not handle it with determinants, okay, no way you can compute it in any computers. And many times also these problems, practical problems and applications do not require you exact computation of all of the eigenvalues and eigenvectors. Sometimes you need only dominant one, like biggest one, strongest one, an eigenvector, which corresponds to that particular value, okay? You don't need all of them. And sometimes you need them approximately, so you don't really care if they are very precise, but they could be close enough for your practical applications because your data are noisy. So who cares if you get the plus minus some tolerance? Doesn't matter that much. Okay, so you don't need exact algebraic solution, which exactly solves the system. In most practical cases, you need approximate solution for a system of equations. Good enough, all right? And you also have numerical tolerance. You have some other tolerances in measurement of your data that you have. So it's all not that important that you will solve that with determinants. So here are a few, I will show only a few of the methods, how you can solve it numerically and find important things for determinant, for eigenvalues. You have probably like dozen more of different methods to compute eigenvalues. They are getting better and better, and this is, I believe, still active research area where people try new algorithms to find eigenvalues faster, better, closer to the real values and so on, especially for huge matrices. Okay. So here's the idea. First idea is power method. Power method seems to be trivial, but it has intuition behind it, which I will show. We'll get some glimpse into intuition of that thing. And it seems to be like completely crazy and makes no sense whatsoever when you just look at it initially, okay? But just bear with me, this works. Okay. Very interesting method, very simple method. And it also connects us to all kinds of state space systems. It connects to multiple other things. So here's how it works. Let's say you have, first of all, I will do some definitions, okay? Like what I'm looking for, okay? What this method is actually doing. So number one, you have matrix, which is general complex square matrix with some eigenvalues, complex or real, whatever. It's diagonalizable. This is my assumption for that particular method, that you have diagonal representation for that matrix. And most of the matrices that we are working with are diagonalizable, so it's fine. And I will sort its eigenvalues from the biggest one to the smallest one. Okay, so biggest one I will call S1. Okay, this is my biggest one. And I will also assume that it is bigger than all of the rest, which means you don't have second biggest as well. Like you don't have two equal biggest eigenvalues, which is, again, most of the cases are like that. Sometimes you have two eigenvalues which are the biggest ones and it's the same, but this is rare. Okay, so this is the method which will work for that type of thing, where you have one possible biggest eigenvalue, absolute value of that value will be the biggest one, which means if you have eigenvalues of like -8, 5, and 3, so biggest one is -6, because we are talking about magnitude of that number, not the absolute value, which is magnitude, not the actual value, because -6 is obviously more negative than 5. But magnitude of -6 is bigger than magnitude of 5. Okay, absolute value is bigger. So this will be my S1 that I want to compute. All right. Now, We will call that value dominant eigenvalue, and the corresponding eigenvector we'll call dominant eigenvector of that particular matrix. And this is what we want to find with that method. Here's the method. This method will tell you, you can assume right now that k equals to 1 for simplicity. So you're just taking random vector x, whatever that vector is, you multiply it by matrix A, and you get next vector, next iteration. Then you do the same thing for that new vector. You multiply from the left by matrix A, and you get new vector. Again, multiply from the left by vector A, that new vector, get new vector. And you iterate on that multiple times. So what happens is, first time you multiply by matrix A, right? Second time you multiply already by matrix A squared, the original vector. Then A cubed, A fourth power, like all this higher and higher degrees. So you get A to the m's power, whatever it is, at particular m's iteration, multiplied by your original random vector. Okay, completely like you just pick random vector. You need to pick, the only rules that you need to pick vector, which is not orthogonal to actual eigenvector. Okay, this vector needs to be random enough not to correspond to one of the biggest eigenvector, okay? Like if you guessed it from the beginning, then it won't be that interesting. But typically you can't, okay? So any random vector will be fine, all right? So my claim is, if you do enough of these steps, you will converge to the dominant eigenvector. Makes no sense, right? It's like you start from some crazy random vector, you keep multiplying by matrix A, multiplying. I'm saying like no matter where you start, you always will converge to the dominant eigenvector, which corresponds to the largest eigenvalue. Why is that? Any ideas how it works? Why eventually you will converge to that thing? And by the way, that type of system of equations, this is practically a system of equations, right? It's state space and discrete state space. You have a lot of that in modern control. That type of systems, you have that in estimation theory, you have that in computation of Monte Carlo, like MCMC. You have that probably also in power systems, maybe. I'm completely sure, not my area. But everywhere you have state space, you have that type of equations, okay, to solve. But this is used for completely different purpose here. All right. So we'll have that xt starting from random vector. You can choose particular vector if you want to. And we will call x to the t, this will be iteration number. So t will be not time, it's like 1, 2, 3, 4, 5, and so on. Just integer numbers. To clarify here. Now, typically in the actual algorithm, so this is supposed to work, okay, as is. But it will have a lot of numerical problems. Why? Because if you're doing powers of matrix A, it becomes sometimes bigger and bigger. So numbers will grow and grow and grow inside of that matrix, and they will become like billions, trillions, gazillions, whatever. So computers cannot represent that kind of numbers, and especially when you need to solve that type of thing, and you multiply by these huge numbers, you will have a lot of numerical error in it. So the numbers, the vectors will become too big or too small. They will converge to 0, and the tolerance will be too small to represent something very close to 0. Or it will be like too huge and you cannot again represent it in computers. It will take too much of your memory, or you will have overflow of some kind in computers. So what people proposed is to multiply it by some constant, because it doesn't matter where you start. So if you multiply that original vector by some constant, it still who cares, right? You can multiply by any constant. So each iteration when you multiply by a, you normalize in vector a to have norm 1, just divided by its own norm. Right? You just normalize in that vector to have values not moving out of the unit circle. So they're always sitting on the unit circle, because all you care is direction in eigenvalues, eigenvectors, right? You don't care about like constant, which multiplies that eigenvector. So you can keep it also always orthonormal to other things, okay? So you're keeping it normalized all the time, that vector, because you care only about direction, not about the actual magnitude. So why this direction would converge to something? Okay, this is the biggest question. Okay, my claim is that it will always converge when t goes to infinity. Okay, it will converge to the dominant eigenvalue, and we will derive it next time why this works. Right? Any questions so far? Yes.
When you compute these eigenvectors in MATLAB, when you plot it, you say that they have units. Sometimes they differ, so those units that does not matter. When you compute the eigenvectors, it does not really matter. You can just normalize it.
You can scale it by any number you want. You can multiply it by any number you want, including its own norm or whatever. Yes, so eigenvalues are defined up to a constant. And you have infinite now, and this is why they're called eigenspaces, right? Because you can multiply them by any constant, which will create linear combination, and then it still will be eigenvector, right? Because again, A times V equals S times V. So if V on both sides multiply by any constant, it still will work. Still, like this number could be cancelled on both sides. It still does work, right? Any other questions? All right, thank you. Today we'll continue talking about eigenvalues, eigenvectors, their applications, and numerical computation. So we started already to talk about power methods for computation of eigenvalues. And the reason was that we just don't want to compute determinants because they're too computationally expensive. We cannot do that. But before we go to that, I think I've got very interesting question and very important question from the previous time you probably were too shy to ask. But I assume that many of you might have same question about eigenvalues and finding orthogonal eigenvalues, because we computed eigenvalues of the matrix R. All right, if you remember, this was J1 and 1J. These are the eigenvalues. And then I said, well, to make this eigenvalues orthogonal, you need the matrix to be normal. And to make it normal, you need that matrix transpose times the same matrix will be equal to that matrix times matrix transpose, which means transpose could switch sides in a sense. And then it will be normal, and then all of the eigenvalues, eigenvectors will be orthogonal. But if you just look at the eigenvectors, you can easily prove that R transpose R equals R transpose R. Very simple. Okay. So in the left upper corner, you will have cosine square plus sine square, which is 1. Everything else will cancel out. Everything will be nice. This will be very normal matrix, beautiful matrix. All right. And eigenvalues, eigenvectors were, I believe, something like that. First one was J1, second one was 1J. And then we said, obviously, they are orthogonal because this is normal matrix. Are they? Why do you think they're orthogonal? How do you compute orthogonality? Dot product equals to 0, right? So what is their dot product?
2J. 2J.
So it's this one by this one.
1 over 1 plus.
Is it 0?
No, it's 2J.
No, it is 0. This is a tricky part. Because dot product for complex vectors. That's thing. It's conjugate transpose of the vector. So taking conjugate of that thing, which will be minus J1 for the first vector, and 1 and J, which will be just J minus J equals to 0. Okay. So for complex functions, we always define that as Hermitian transpose or conjugate transpose. This is what dot product is for complex vectors. Because previously we defined that only for real vectors, which was just transpose. But everywhere that you see transpose and you have something complex, you always use H instead of T. Okay? Always conjugate transpose for everything in linear algebra. Okay? The cases where you're actually using transpose on complex matrices is extremely rare. And it's only when you need to reorganize columns as rows, nothing else. Just in data analysis, sometimes you just need to reorganize columns as rows or vice versa. This is the only case we're using transpose for complex vectors and matrices. Everywhere else you're using H, conjugate transpose, right? Let's record what I wrote on the board. Picture of that. Now we can go back to the power method. Power. So we got to the power method, which says if you can organize eigenvalues in descending order, which means it starts with the biggest one, and we'll call that, we mentioned, dominant eigenvalue. And we want to find mainly the dominant eigenvalue. We don't care about all the other eigenvalues. And we want also to find dominant eigenvector, which corresponds to that eigenvalue. So we have very simple procedure for that. Numerical procedure, which is not requiring us to do any complicated computations. It's just iterative. You can just multiply by matrix A any random vector, whatever it is. And if you have single dominant eigenvalue, then it will converge to that eigenvector. Okay? So you multiply by powers of A, higher and higher power of A. Eventually, you will get to good eigenvector, which corresponds to the biggest eigenvalue. This is what you plan to get. So these are the iterations. And then we also said that to prevent that vector to diverge or converge to zero because of numerical approximations in the computers, we also want to normalize that vector, let's say by norm of its own norm. It means it always will stay on the unit circle. And since for eigenvectors, we don't really care about the magnitude of the vector, we can pick any magnitude, including magnitude 1. All right, but it was not very clear why you would start with any vector and eventually it should converge to the biggest eigenvector. Like, why would that be the case? This makes kind of no sense. It's very surprising, I would say. Like, first time you see it, it's very surprising. So I will try to show you mathematical reasons for that, which is actual computation, which shows you that it should converge eventually when t goes to infinity. It should converge to the dominant eigenvector. And also I will try to show two-dimensional simple case where in 2 dimensions, I will show you that it is converging to that particular bigger 1 out of 2, obviously, eigenvector, okay? Regardless of where you start with it, okay? It doesn't matter. And there will be also additional condition, like when it converges and when it kind of oscillates around, it's not always converging. So I'm saying like, well, it will converge. Not really, not always. It depends. There's many different things in math. You need all kind of conditions for that to be satisfied. But in most cases, we will just ignore most of these conditions and just use that method and get whatever we can get. Okay, so here's what we want to derive here. The idea is that we want to develop that method and to see that all of these eigenvalue, eigen iterations on that equation of next x equals a times previous x will converge to the biggest eigenvector. Okay, so this x from any kind of value will converge to whatever we want it to be converged. So that limit of t goes to infinity on these iterations, t equals 1, 2, 3, 4, 5, 1 million, whatever iterations you need, it's converging to that dominant value. So let's see how it goes. So we have some matrix, which could be, in general, some sort of complex matrix. And it could be any kind of square n by n. Any given complex matrix. And we want to find eigenvalues. And we will assume that it is diagonalizable. All right. We also assume that you have biggest eigenvalue, like 1. unique biggest eigenvalue in absolute value, which means magnitude of the eigenvalue is uniquely biggest. So you have only one like that, not 2, 3, or 5. Only one. Okay, this is unique. And then what we can say that eigenvalues are given as S1, which is bigger than S2, or equal S3, and so on. Okay, you can rank them by magnitude. So, the eigenvectors will be written as the following. I have to do it that way. Let's simplify. So have eigenvectors, let's say xi. Okay. So you have n eigenvectors. Since the matrix is diagonalizable, you have all of them normal. Okay. They create bases for any vector. So you can represent any vector as linear combination of these eigenvectors in some way. So they could be giving us some sort of representation for x0. Okay. So that representation of x0 will be some sort of alpha 1, x1 plus alpha 2, x2, and alpha n, xn. All right. So just writing that in basis, eigenbasis. Right. So this is possible to write always. So you have that kind of coefficients alpha 1, alpha 2, alpha 3 for that given initial vector, and this could be any random vector in that subspace. Right? All right. So now we will apply iteration to that thing. And let's see what happens. So the point is that I want to replace multiplication by matrix A by multiplication by that scalar n vector. Right? This is what eigenvalues are for. So what will happen to A x0, which is practically x1? Right? This is what we started with. x1 equals ax0. This is first iteration. So what it will be? So ax0 will be A times all of the things. Right? So it will be A times alpha 1 x1 plus alpha n xn. But what is alpha A times alpha 1 times x1? What is that? So this is eigenvector. A times eigenvector, what is that? By definition, eigenvectors times any vector. This is how eigenvectors are defined. So it's eigenvalue times the same vector, which means that this thing would be written as alpha 1 s1 x1 3 dots alpha n s n xn. Now these are numbers now, scalars, no matrices here. By definition of what A times that thing means. And again, this is scalar, so you can take it out. You can change the order, right? Because it's not matrix multiplication. This is matrix by number by vector. So number can go out of parentheses. So you'll get something like that. Right? Okay, so far? Okay. So after m iterations, so what happens after m iterations? So this was first iteration, now you repeat the same thing multiple times. So you again multiply that thing by a from left. Okay, what will happen? This will stay the same. This will have second power because you again multiplying by S1, right? This will stay the same. So practically you'll have the same thing, but in m's power after m iterations. Okay, so what you'll have alpha 1 S1 to the power of m x1 plus alpha n Sn to the power of m xn. That's what you get. All right. Now you can say that this thing, which is practically nth iteration of that thing, equals to that thing. All right, so far? Okay, so what is that thing? Let's write it differently. Let's take alpha 1 and S1 to the power of n out of parentheses. And then what you'll have in the parentheses is x1 plus alpha 2 divided by alpha 1 S2 divided by S1 to the power of m plus and so on plus alpha n divided by alpha 1 as n divided by S1 to the power of m. And you need to multiply all of that
by x.
X2, this is x and right? Something like that. I just rewrote the same thing in a different form, different shape. So let's see what happens here. So first thing, this is some number times some other number times some vector, which is x1. And x1 is dominant one because we know that S1 is the biggest one, right? Now, what happens to that thing when m goes to infinity? So we know that S2 is smaller than S1. Okay, so if you divide in something smaller by something bigger, you get something less than 1. But to the power of m, which is kind of becoming higher and higher powers of that 0 point something number, or minus 0 point something number, where it will go?
Less to 0.
It will go to 0. Okay, so limit of that thing is 0 regardless of what this number is, and so on. Like for high enough m, it will just approach 0 eventually. Okay, same thing with all of the other terms because all of them becoming even smaller and smaller, right? Because you sorted them in descending order. Okay, so higher s indices means smaller s magnitude, which means this ratio will become smaller and smaller. To the power of m, it will become even smaller. Okay, with bigger m. So all of these terms
You have x.
will be written like that. So it will be alpha 1 S1 m. And we used to write it as O, big O, which is smaller terms of that order of magnitude, which is S by S1 power of m, something like that. So practically you get linear convergence, which is not super fast. You will not get very fast convergence, but you will get some convergence eventually with m. So you just iterate enough times, and then you will get practically to that thing. But what is that thing? This is exactly what you're looking for. This is a dominant here is an eigenvector. So this is some number times dominant eigenvector. And if you normalize it by 1, you get dominant eigenvector with norm 1. That's it. Okay, so you eventually will converge to dominant eigenvector x1. And that's exactly what you want. Okay, because all of the other terms will be very close to 0, so you'll disappear eventually. All right, so this is proof of why this method works mathematically, but still not giving you too much of the geometric intuition of what happens in that kind of situation, like why they kind of all disappear suddenly. Okay, so mathematically, this is what happens. But I will show you also the geometric approach here a little bit later. And before we get there, here's the procedure. Here's that. The procedure is very simple. You're normalizing at each iteration, you're normalizing that vector, making it norm 1, just by dividing by its own norm. And then you're doing that iteration and repeating that multiple times. This is criterion, just stop it. And you have multiple different criterions, actually. You have multiple criteria to how you stop it, like when should you stop your iterations. If it is converging, which means the difference between the next iteration to previous iteration is less than some threshold that you decided on, that you're saying this is my tolerance, epsilon. And if the difference between the next iteration and previous iteration is smaller than that epsilon, you're saying, well, it converged, right? Now, the convergence actually happens when the biggest eigenvalue is positive. When it is negative, it is still giving you some idea, approximation for the dominant eigenvector, but it might oscillate. And this might be a problem, okay, for some of the computations. So if your biggest eigenvalue is negative, it doesn't have to converge, really. So it's a little bit tricky, and you have other methods which are helping you to figure out what to do in that kind of cases. So now we have the biggest, or corresponding to the biggest eigenvalue, eigenvector, but you don't have the eigenvalue. How do you compute eigenvalue? That's the question, right? Now you have eigenvector, you don't have eigenvalue, dominant eigenvalue. That's what we want to find. And this is a formula that you can use for that. It's called Rayleigh quotient, and relatively simple to compute if you have that eigenvector and you have matrix A. This will be the formula. So you're just multiplying at the given iteration, you're multiplying Hermitian transpose of that vector, which is conjugate transpose by matrix A, multiplying back by that vector, and dividing practically by Hermitian transpose times the vector, which is dot product between X to itself, which is norm squared practically. Okay. So you're dividing that kind of norm to that kind of norm. Both of them are actually norms for particular A's, but this doesn't have to be norm. So this is, you have name to it, and Rayleigh was a very famous person actually in physics, not in linear algebra, and he had Nobel Prize, and he developed multiple different things in optics and waves and what's not. He has like multiple different things on his name. I believe he also discovered argon gas. So he worked in gases as well somehow. This is like new element. He developed new element, chemical element, which is a gas, argon. But this is what we know him for in linear algebra. Okay? This kind of quotient, which is used a lot in multiple different applications. And you can even start iterating instead of power method, you can iterate on that kind of thing. And then to find dominant eigenvalue first, and then from that to find eigenvector, which corresponds to that eigenvalue. So you have other methods to find dominant eigenvalues and eigenvectors. All right, so how do you get there? This is the question. So the derivation is relatively easy here. How you get to that formula, why this formula works, in a sense. Okay, so let's see why this works. Here. Okay, so what the claim is that S1 will be equal to X1 boundaries T and transpose AX T divided by X T transpose X T. This is the formula for Rayleigh quotient. So why that works? So if X1 is dominant eigenvector, what happens to that part? What is that part?
It's just alpha 1, S1.
So this will be just X1, H,
There.
S1,
Yeah.
S1. Right? But S could move outside here. This is a scalar. This is just number. So you can manipulate. It's not like matrices. So if it is number, it can jump out. So you'll have that thing here and these two things there, which are exactly the same. They cancel out because look, this is number. And this one multiplied by this one is number. This is dot product. So this dot product divided by itself will be just one. You'll have that one as one. That's it. Okay. This is simple. Any questions on that? So everything just by definition.
We got the AX1 from this, right? The AX1. We got it from here.
This
So
is that iteration, t's iteration when t is big enough.
yeah. So
For t not infinity, it will be just approximation of S1. So it will be approximately S1. But for t goes to infinity, it's supposed to converge to S1. Okay, so it's approximated value.
so why don't we take the alpha with it? The constant.
Alpha is not
So
this constant that you need. You
The
need
eigenvalue, no?
alpha to the s to the power of
Yeah.
n. And you don't know what that is. So you want to find S1. It's like, would be circular if you take in that part. You don't know what that is. You know the eigenvector, but eigenvector could be proportional. It could have any coefficient of proportion, right? It could be 5 times eigenvector, 1,000,000 times eigenvector, still same eigenvector,
Same
right?
eigenvector.
But what's the eigenvalue corresponding to that eigenvector, which could be any length? So this is length of that eigenvector. So it's not telling you anything about eigenvalue. So this is that eigenvalue corresponding to that eigenvector. Okay, any other questions? Okay. All right, so what is the intuition behind that method? This is additional interesting and visualization of what we want that to look like geometrically. So let me draw, first of all, unit circle in regular system of coordinates without having any other thing in it very well. Let's see about it. Just a second. Okay, so we have that system of coordinates. And we are talking about two-dimensional 2x2 matrix. With particular eigenvalues, I will have unit circle like that. I'm great at drawing circles, but that's okay. All right, and you will start with particular vector. Let's say something that this will be your x0. Okay. Now you have your system somehow scaled and rotated. Remember what happens to eigenvalues? They create also orthogonal system, but it's somehow rotated and scaled compared to your original rectangular system. So you have some other axes, whatever they are. Let's say something like that. Use other color, but your V1 and V2. Eigenvalues, directions, eigenvectors, directions. Right? And if you remember how you compute in eigenvalue space, you project Remember we did it previous time, you project to the axis and scaling it by S1 in that direction and scaling it by S2 in the other direction. And then you get new vector. So let's see what happens. So we have these projections. I think the one. Okay, so you have these points. And let's say V1 is the dominant one. Okay, so you will scale it by that vector, you will scale it by S1, which will be, let's say, twice. Okay, will be somewhere here, that axis. And this will multiply it by 1.1 or whatever, something smaller. That will be here somewhere. All right, just example. So what happens is the result will be that vector. This is new vector. Now, this is my step of multiplication by matrix A. And after multiplying by matrix A, I will get that point here. Second step is normalizing it again to the unit circle. So this circle is 1. 1 minus 1. Oh. So I'm projecting it back to that point here. Right? So I have that new vector is here. And I'm repeating that multiple times. I'm again multiplying by matrix. I'm getting projection here, projection there, multiplying that by a little bit, multiplying it by long, projecting it back to the circle. So what happens to that point on the circle, where it will move, regardless of where you start? Since you're squeezing that space more than this part, which means you're stretching that more in that direction, this part always will be longer than stretching in that direction, which means it will move slowly to the axis, okay? So eventually, it will go that direction somehow. It will get closer and closer to that axis until at infinity, it will actually hit the axis, okay? All of the other dimensions will be super small, because here you will have just a little bit, right? So your projection will be like that. This projection will be like that. So you're multiplying that by a small thing, like plus a little bit. Here you multiply it by twice, which will be probably like far away here. Okay, so this vector will be like that. So it will be even smaller, and so on. So every iteration, you get closer and closer to V1. But V1 is your exact dominant vector. This is exactly what you do. Okay, so regardless of where you started, since you're stretching here more than here, it always will be tilted to that axis from any point, regardless of where you start. This is the idea of power method. So by multiplying by matrix A, you're practically pushing that vector to the V-axis. That's it. This is the geometric intuition behind that method, like why it works. Any questions?
Okay, so if you kind of write a simple code up, let's say xn is equal to a times x1, and you repeat this multiplication, over several times, xn will be the dominant eigenvector.
Yes. Great idea for the homework. Do that in the code. And we will do that in the code. You just iterate on multiplication by matrix, you get the eigenvalues that you want and eigenvectors that you want. Okay, but this is only the dominant one. What happens to other ones? Like how do we get other ones using similar idea, but not exactly the same idea? A little bit more complicated, but you still can find all of the other eigenvalues and eigenvectors of your system if you're using same kind of ideas of things which are not changing eigenvalues. And this is the overall idea. You can extend that power method for example, minimal eigenvalue first. How do you do that? You sort all these eigenvalues again in descending order, and you want to find the Sn, which is smallest one out of all of the eigenvalues that you have, again, magnitude-wise. You know that spectrum, which are eigenvalues of matrix, inverse matrix, are 1 divided by eigenvalues of the original matrix A, which means that the biggest one of the A inverse will be the smallest one of A, practically speaking. So compute A inverse and do power method on A inverse. Okay, so you'll get smallest one. So that's one of the ideas, which is called inverse power method. You just invert in the matrix, and you know that this is like solving system of linear equations, which is not too complicated, not like determinants, which are recursive. So this is computationally not that expensive. Solving system of linear equations is pretty fast in computers. And then you're finding inverse of that matrix. And for that matrix, you're doing power method, which is iterating like 10 times, and then you get minimal eigenvalue. But this is not all, because you have typically more than that, unless this is 2 by 2 matrix. So here's a trick, okay? The trick is that eigenvalues of the matrix I, A minus some number times I, which is identity matrix, are just S1 minus that row number. Okay, so all of the eigenvalues will be shifted by row if you're subtracting I times row from that matrix. Very interesting property, okay? And you can easily show that just by determinant as I minus A, and if A is also equal to like new A, AT, or whatever you call it, is A minus row I, obviously SI minus row I, so S will be shifted by same row. Okay, so that's a very simple relation between the matrices. Okay, if you're subtracting something from main diagonal, some constant, your eigenvalues of that matrix will be shifted by the same number. Okay, very easy property. So you can use now that property by guessing some values of eigenvalues in a sense. Practically, you will find the closest to row eigenvectors corresponding to that eigenvalue of row. So here's the thing. You don't really need to know them. You don't really need to guess them. You can just scan through multiple different numbers, okay, from biggest one to smallest one. So you found already smallest one, biggest one. So you know what is the range where you need to scan it. And you know how many of them need to be there, because it's exactly n, right? Depends on the size of your matrix. And each time it will converge to the closest one to row. All right? So this is how computationally it is done. And this is called shift in inverse approach. Why? Because what it means to be closest to row, you cannot use power method anymore, because this will not be the largest one. It will be closest to 0. Because if your eigenvalue is very close to row, the difference between S1 and row will be as close to 0 as possible. Okay, so you need to use inverse method here to compute all of these eigenvalues with row. So here's how it will go. You guess the initial value, whatever it is, in the range from biggest one to smallest one. And let's say it's like Si, whatever that value is, for some I. And then you're doing the inverse power method, which is, again, same step, normalizing to norm 1, your guessed vector, whatever, random vector. And then next thing, you invert in that matrix, A minus row I, which is inverse method, okay? And then multiplying by xt and iterating on that many times until it converges to something. So this is a summary of all of these 3 methods. So first method, you're just taking x, normalizing it, multiplying by a, and rotating in that loop, normalizing, multiplying, normalizing, multiplying. This power method. Inverse power method, you normalizing your initial random x, multiplying by a inverse, and iterating, normalizing, iterating, normalizing, iterating. And this is that shifted power method, which is you're also giving some guess for the original location of your in the middle type of eigenvalue, and then you're iterating on that thing, as explained here, right? So these are the ways to find all kinds of eigenvalues numerically. Any questions? Okay. So we have different method to compute eigenvalues, which is called QR method. Very interesting method. I will not go into details of that method, but I will just explain the overall idea, like what we do there. And this was developed same year by completely independently by one Soviet mathematician. She was kind of known professor already. And another mathematician, British mathematician, John Francis, who haven't even completed his degree. Okay, he dropped out from his degree. And the interesting story here is that he didn't know how much effect his method gave to all the development of linear algebra and many other disciplines. So QR method, QR decomposition method. I mentioned that when we talked about LU and QR, if you remember, on solving a system of equations. So this method got top 10 ranking in the most important algorithms of 20th century. Okay, there was some ranking of different algorithms which were developed in 20th century. This is in top 10. Okay, this algorithm. So John Francis discovered that only 45 years later, somebody, like one famous mathematician, actually found him somewhere when he was already retired and like fishing somewhere. He found him just to tell him how famous he is. He never knew about it, that his QR method is so famous, and that he developed that maybe like 60 or something, 1960. Only in 2005, somebody found him just to tell him how famous he is, and he's in Wikipedia, obviously, and other places. He didn't complete his degree, and then he got his like honorary doctorate degree and other accolades, 45 years later, after his algorithm became famous. He didn't know he was an undergrad student at that time. So here's the thing, you can find all of these eigenvectors at once. And the idea is that, like overall idea of the algorithm, that you can apply something similar to power method, but for each eigenvalue separately, and write it as a matrix stuff together. So you multiply into matrices. And also at each step, you're not using just normalization by norm, but you're orthogonalizing that vector from everything else. So making it as different as possible from all of the previous eigenvectors that you already iterated on, which means it will give you all of the orthogonal directions and they will develop kind of separately in each direction. But technically it works in a very simple manner. Okay. And here are algorithms by Koblanovskaya and Francis. You start with your original matrix and call it A0. This is your zero iteration on the matrix. Okay, so now you're not iterating on vectors, you're iterating on matrices. Okay, you're doing QR decomposition, and just to remind you what QR decomposition is, it's multiplication of two matrices. You write given matrix, and you always can do that, as multiplication of Q matrix and R matrix. So R matrix is right triangular matrix. You can call it U. Previously we called it U, upper triangular matrix, okay, or right matrix. You have some numbers on the right triangle, upper triangle, and zeros below that main diagonal. Okay, this is what matrix R is. Q is very interesting matrix because it's orthogonal matrix. So Q transpose Q equals I, similar to our rotation matrix, okay, that kind of matrix. So Q inverse equals to its own transpose. This is that great property of Q matrices. Okay, so you can always decompose any matrix into matrix for which transpose is its own inverse, and triangular matrix. Okay, this is these two matrices, okay, that you decompose it to. So now you have that A0 equals Q0 and times R0, which are two matrices of that kind. And then you repeat the following for n steps again until it converges to something more or less triangular. And why do you want it to converge to something triangular? Because in triangular matrices, eigenvalues are sitting on the main diagonal. This is how it works, similar to diagonal matrices. All the eigenvalues will be just sitting on the main diagonal for all triangular matrices. All right? It's very simple. If you get triangular matrix, you can just read the values. You don't need to compute anything else. And so far, yes.
So when you first decompose into Q and then R, are you doing the iteration on Q?
You're not iterating on anything. You have like some constant matrix that you start with, and this is your original matrix. You just decompose it as Q times R, so you get two other matrices which are describing the same original matrix, and they're constant matrices. So it's still not iteration. I just call them Q0 and R0 because I will do the following iterations that you have in green here. Okay, so I will have two steps. I will say for steps t equals from 0 to whatever integer number until that matrix is near triangular, and I'm not proving why it will become near triangular, but the values below the diagonal, below the main diagonal will become closer and closer to 0, similar to power method. And we'll use practically the same ideas. And I'm, again, not proving it, I'm just telling you that all the below diagonal values will become closer and closer to 0, so you'll have approximation of triangular matrix. So the main diagonal values will become closer and closer to your actual eigenvalues of the matrix when that happens, naturally. If you're not changing the eigenvalues in the process, okay? So if all these iterations are not changing, not modifying eigenvalues of your matrix, and you keep same eigenvalues for each iteration, then this diagonal values will become your eigenvalues. This is overall idea. So these are only two steps, okay? So this is your first step, like here. You're just writing AT equals QR decomposition, and then you flip the order, R and Q. You multiply R by Q, and this will be your next iteration of your matrix, okay? Sounds a little bit tricky. Again, you have regular decomposition. This is like QR method to decompose that matrix A. You get it as multiplication of two other matrices. You flip the order of these matrices, and you get new iteration for your new matrix. My claim is that these two matrices have exactly the same eigenvalues. Okay. Why do you think this is the case? Why QR and RQ have exactly the same eigenvalues? Any ideas? How would you get to that? So AT and AT plus 1 have exactly the same eigenvalues, and the claim is that eventually this will become triangular after enough iterations. So obviously they will have exactly the same thing because you started with your original matrix, and you haven't changed eigenvalues in the process, so you get the same thing. Compute all of them together as main diagonal values for the AT goes to infinity. So why they have the same eigenvalues is the question. Okay, let's see that simple proof. Okay, so here is a claim. A equals QR. Just regular decomposition. For any iteration, it will be the same, so I'm not even writing indices of iteration. B matrix equals RQ. Just flipped order of the matrices. So I'm taking same matrices, exactly same matrices, flipping the order and defining new matrix B, which is different matrix, obviously, from A. But my claim is that A and B have exactly the same eigenvalues. This is a claim that I want to prove. So how do I do that? Okay, so what happens is, if I do multiplication, like I'm starting from that one, I will multiply by Q transpose from left. Both sides. Haven't changed anything yet, right? Just multiply by the same matrix from left and from right. But what is that?
I.
It's I, because this is orthogonal matrix, so this is I. This is I. Okay. Now, what is Q transpose A? I'm multiplying both sides from the right now by Q. B, R, Q. right? Okay. But what is RQ? It's B. What is Q transpose for orthogonal matrices? It's Q inverse. It's Q inverse AQ equals B. Seen that kind of expression before. What is that expression? What is that transform? It's similarity transform. And similarity transform, we show that for any similarity transform for any invertible matrix, you have same eigenvalues. So A and B have exactly the same eigenvalues. Right? This is the idea. Questions on that? And as I said, you just iterating that multiple times, you get diagonal eigenvalues, and that's it. And you're done with that simple method. Derive that. And as I mentioned, all the values below main diagonal will become closer and closer to zero, so it will become more and more triangular. All right, another fun theorem with which I loved to play when I was doing my master's degree. Very interesting theorem, how you estimate or approximate location of eigenvalues without actually computing them in very, very simple form. And that's called Gershgorin circles theorem. He died very young, age 32. But he developed that beautiful theorem which allows you to estimate location of eigenvalues without computing practically anything. You just given the matrix, all you need to look for is diagonal values and sum of all of the rows and columns. So that's it. This is how it works. So you need to draw circles for matrix n by n. You have some complex, n works for complex matrices similarly to real matrices, okay? It works for any kind of matrices, which is even more beautiful, this generic. So here is the theorem. Theorem states something like that. Take all of the diagonal values, and these diagonal values will be your center points. And they could be complex, or they could be anywhere not on real axis. They don't have to be on real axis. But for real matrices, they will all be on the real axis. This will be just numbers, right? Main diagonal values. So this will be like middle point of your circle, center point. All right, so far, these are diagonal values, are center points of your circles. Radius of that circle is the rest on the same row. So you're taking, for example, let's say you have that matrix, a 3 by 3 matrix, okay? So your location here of the center point is 10, which will be probably somewhere here, like close to the black dot, but in the middle of the circle, okay? So it will be here. This is 10, and then you add in 2 plus 3, this will be radius of your circle, which is 5. So this is a big circle, radius 5, and center at 10 here, all right? Second circle will be, from that matrix, will be located at 2, which is that thing, okay, somewhere here. And the radius will be 1 plus 1, which will be 2, okay? So it will be 2 with radius 2. So it will be the small circle inside, that kind of circle, okay? Third circle will be located at 3, which is somewhere here probably. And radius will be 1, because it's a sum of 0 and 1. That's it. This is the theorem, okay? Now you can add to that corollary, which is also theorem in a sense, but which it kind of, you can prove it easily from the first theorem. And the corollary is based on the very simple property that eigenvalues of A transpose are exactly the eigenvalues of A for any matrix. Okay, so you can transpose a matrix, you'll get exactly the same eigenvalues because A transpose is always similar to A. Right? You have always similarity transform between A and A transpose. So what happens is that instead of computing sum in the rows, you can compute sum in the columns. But eigenvalues need to be in the overlap of the circles, of sums and columns. Okay, and this is why you have kind of some of the circles are kind of going that way, and some of them are going that way. So it needs to be in shaded area in both directions where you have crossing between these two. And this is what happens. So let's look at the first one. So first one is radius 10, and not radius, location 10, which is here, okay, somewhere here, and radius 5, and radius 1, okay? So this small circle is radius 1, and this big circle, radius 10. So only in overlap you can get it. Eigenvalues have to be in the overlap of these two circles. Same thing with the 2. So you have center 2, which is, again, somewhere here. And then you have radius 2 and radius 3. Okay, so you have that radius, which is that circle. And then radius 3 will be that circle, the bigger one. Okay, again, overlap will be that cross-shaded area. And third one will be location 3, which is somewhere here, right? And radius 1 and radius 4. So radius 4 will be that big circle, and radius 1 will be that small circle. Again, it should be somewhere in shaded area, but this doesn't matter because it's already included in the previous one. So you have that already inside of that bigger circle. So all of your eigenvalues, regardless of matrix, have to be in cross-shaded area. And these black points are actually showing you the actual location of eigenvalues, real eigenvalues of that particular matrix. All right? So you can estimate where they're supposed to be without any computations, really. It's like minimal computationally expensive. You have very simple way to estimate where they should be. And interesting things that you can extend the theorem, and this is what I played with. What are the other criteria that you can use just by basic similarity transform? Because similarity transform is just inverse matrix times a matrix times another matrix. You clearly will have different diagonal and different sums of the values in other places in the matrix. But each time you get new theorem, in a sense, because new property, and it has to overlap all of them. Okay, so all of this overlaps of all of the circles with any transforms, any invertible matrix can give you new circles by similarity transform, and then overlaps of all of the circles, so you can get closer and closer. What will be the best one? What is the best transform that you can use? Which is not very useful because you cannot guess it, because this is the entire point. What would be the best case here? Where the radius is 0, practically, right? Then you will have exact location of the eigenvalue. So what that transform will be? Diagonalization transform. If you're diagonalizing, your matrix will be diagonal. So the location of the circle, like center of the circle, will be main diagonal values, which are eigenvalues already, okay, by definition. And some of the radiuses will be all 0 because it's a diagonal matrix. Like everything else will be 0 in that matrix. So it will be circle of size 0. It will be exact eigenvalue, but again, that's not very practical because you don't know what the transform is. For that, you need to find eigenvalues first and eigenvectors. And then you can find the diagonalizable transform, because this transform is practically eigenvectors as columns of that matrix T. Remember that? How to diagonalize matrices, you just put in eigenvectors as columns. So you technically need to find eigenvectors to find that invertible T. It's not very practical because the entire point is to find, to approximate the location. Okay, so this is the overall theory about that. And last thing on that topic is how you actually find roots of polynomials, because this is a very interesting topic and people typically do not think about that before they come to numerical methods courses, because they just give to MATLAB to compute roots of whatever polynomial. In practice, there is no formula for any polynomial higher than degree 4, okay? This is Abel-Ruffini theorem, which states that there is no way to find analytical formula which will describe roots of polynomial of order higher than 4, like 5 and higher. it's not just we don't know it, okay? It's much more horrible than that. Because if we just don't know it, maybe we'll figure it out later somewhere. Like somebody will discover that formula how to solve quintic polynomial, roots of quintic no, nobody will ever be able to do that. You have theorem which is stating there is no way that any, like all roots of generic quintic polynomial could be written as a function of like roots of different kinds or algebraic expressions of different kinds. There is no formula. That's it. Okay? You cannot have that. So this means that the only way to solve most of the equations of a little bit higher power than 4 is just numerical methods. There is no other way. There is no formula and will never be. Okay? It's impossible to find this formula. Again, Abler-Ruffini theorem. If you're interested in theory of groups and other things of that kind, this is where this proof is coming from. Abstract algebra. So we need to find it somehow numerically. And you have multiple different methods to find it numerically, like Newton methods and using derivatives, calculus, and other things, approximating different roots, converging different iteration-based methods. But most of the actual methods which are finding roots in practice are actually based on finding eigenvalues of companion matrices, which kind of very weird. So getting into something more complicated, more complex and difficult. But in that domain, somehow the solution is easier than solving numerically the actual roots of the polynomial. And it's more precise and more accurate, more stable numerically. So if you get into the actual like MATLAB code or whatever, Python code, whatever code is doing function roots, this is what it does. It just gets to solving eigenvalues using power method and other methods for matrices, typically QR methods. This is the most popular method for solving for eigenvalues. So the idea is very simple. You need to find such a matrix, characteristic polynomial of which is your polynomial for which you want to find the roots. Sounds kind of tricky, right? So you're looking for a matrix, characteristic polynomial of which is your polynomial that you want to find roots to. This is the overall idea. And you have two standard forms which are relatively simple, mostly sparse, and characteristic polynomials of these two matrices that you see on the screen are actually those polynomials of s to the power of n plus alpha 1 sn minus 1. You're just writing minus in the first matrix on the left. You're writing minus all of the coefficients on the first row. And this matrix is n by n. And pay attention, the first coefficient is always 1. So this is monomial, whatever you call it. The first coefficient is 1. The rest of the coefficients, you have n coefficients total for nth degree polynomial with the first coefficient 1. You write them minus all of these coefficients. All of the rest are zeros except the secondary diagonal below the main diagonal, okay, where you have all of the ones. So you have all of the ones on the diagonal. You have minus all of the coefficients first row, everything else is 0. And you have similar thing which is practically transpose of that matrix. Okay, so one is called controllable, and second, observable companion form. If you go to my course in modern control, we are using a lot of these matrices there. Okay, there's controllable system, observable system. This is where these names are coming from. Okay, but these are companion forms. And as I said, you just need to find eigenvalues of this matrix, or this matrix, and this will be roots of your polynomial because they have that characteristic polynomial. All right, this is the overall idea. Any questions on that?